A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Alright, here's what Daniel sent us this time. He's asking about context window management in modern AI systems, specifically the gap between theoretical limits and actual performance. So we've got frontier models with context windows up to 1 million tokens, and yet reasoning quality degrades well before you hit that ceiling. He wants us to dig into the mechanisms behind that, attention dilution, lost in the middle effects, recency bias, and then walk through the full landscape of solutions, sliding windows, dynamic summarization, native platform features like Claude Code's compaction command. The key questions he's flagging have front ends implemented transparent auto-summarization without needing manual triggers. Are there projects doing hierarchical memory with different compression ratios for different time horizons? And from a UX angle, should compression be invisible or transparent to users? Does working from summaries rather than raw text affect reliability and trust?
Great set of questions. And I want to start with something that I think reframes the whole conversation, because there's a really important piece of research that most people in this space haven't fully absorbed yet. A paper from Du et al. In 2025 ran an experiment where they replaced all the non-relevant tokens in a long context with blank spaces. The reasoning was, if the lost in the middle problem is a retrieval problem, the model can't find the needle in the haystack. Then removing the haystack should fix it. The needle should be obvious.
And it didn't fix it.
Not at all. Degradation persisted, which means the problem isn't retrieval. It's a function of input sequence length itself. The attention mechanism struggles with long sequences regardless of what the content actually is. You could give the model a single relevant sentence surrounded by nothing, and it still struggles if that sentence is in the middle of a long sequence.
That's kind of philosophically unsettling, isn't it? Because the whole industry narrative has been bigger context. Windows solve memory problems. But if the degradation is baked into how attention works at scale, expanding the window doesn't fix anything. You just have a bigger space in which to lose things.
That's the paradox. And the empirical shape of the failure is well documented at this point. The foundational paper came out of Stanford and UC Berkeley in 2023, the Lost in the Middle paper. They set up a clean experiment, give the model a set of documents where only one contains the answer, vary where that document appears in the context, and measure performance. What they found was a U-shaped performance curve. Information at the very beginning or end of the context is used reliably. Information in the middle is effectively invisible.
So the model has primacy bias and recency bias simultaneously.
Which is already counterintuitive enough. But then Vasselli et al. In 2025 refined this further. They found the U-shape only holds when the context is less than 50% full. Once you cross that 50% threshold, the pattern shifts. The model starts favoring recency above everything else, and the earliest tokens are now the most likely to be lost.
So there's a phase transition at the halfway mark.
The practical implication is almost comically specific. Teresa Torres summarized it well. Below 50% full, you lose the middle. Above 50% full, you lose the beginning. There is no configuration where everything is safe.
Which explains something I've noticed with Claude. Code specifically. You put your architectural decisions or your core .md rules at the start of a session, and by the time you're 2 hours in, it's like the model has never heard of them.
That's context rot, and it's the user-facing symptom of everything we've been describing. The MindStudio team documented this failure mode in detail earlier this month. You start a long session, the first hour is sharp. Tight reasoning, consistent decisions. Then somewhere around the 2-hour mark, the model starts re-asking questions you already answered, suggesting code that contradicts what it wrote an hour ago. It's not a bug in any traditional sense. It's the attention mechanism doing exactly what it does.
By the way, quick note, today's episode is being written by Claude Sonnet 4.6, which I find either ironic or appropriate depending on your disposition.
Probably both. Alright, so given that this is the landscape, attention degrades, bigger windows don't fix it, there's a 50% phase transition, what do you actually do about it? Let's go through the main strategies because they're quite different in their trade-offs.
Start with the simplest one.
Sliding window, or what SWE agent calls observation masking. You keep the most recent interns verbatim and replace everything older with a placeholder, some details omitted for brevity. The agent's reasoning chain stays intact, but the older tool outputs, file reads, test logs, those get masked. JetBrains published a major empirical study on this in December 2025, presented at the Near IPS Deep Learning for Code workshop. They compared observation masking against LLM summarization across 5 different settings, and the results were striking.
How striking.
Both strategies cut costs by over 50% compared to unmanaged context, just letting the context grow freely. But in 4 out of 5 settings, observation masking matched or beat LLM summarization on solve rates while being cheaper. With Qwen3 Coder 480B, observation masking boosted solve rates by 2.6% versus unmanaged context and was 52% cheaper.
So the dumb approach is competitive with the smart approach.
More than competitive, it's often better, which is a pattern that keeps appearing in machine learning. Simple baselines are chronically underestimated. The intuition is that LLM summarization should be better because it preserves semantic content rather than just deleting it. But the JetBrains data says, not reliably.
What's the failure mode of masking, though? Because some details omitted sounds like it creates total amnesia for anything outside the window.
That's the catch. Observation masking slows context growth but doesn't stop it. If you allow infinite turns, the context still grows, just more slowly. And more importantly, the model has zero awareness that anything exists outside the window. It's not, I remember this vaguely, it's this never happened. For tasks with a bounded number of steps, that's often fine. For open-ended long horizon tasks, you can hit a wall.
Which is presumably why people reach for summarization.
Right. The idea with LLM summarization is that instead of deleting old content, you have a separate model, often a cheaper one. Compress the older portion of the conversation into a digest. OpenHands uses this approach, summarizing 21 turns at a time while keeping the most recent 10 verbatim. The Anthropic SDK supports it natively through a compaction control parameter. You can specify a cheaper model, like Claude Haiku, to do the summarization while the main agent keeps running on Sonnet.
That's a sensible architecture. Use the cheap model for the compression work.
It is, but the JetBrains study found a genuinely counterintuitive problem. Agents using LLM summarization ran 15% longer on average than agents using observation masking. With Gemini 2.5 Flash, summarization led to agents running 52 turns on average versus 45 for masking. The hypothesis is that LLM-generated summaries smooth over signs that the agent should stop. The summary makes the agent feel like it's making progress. I've done X, Y, Z, I'm making headway, when actually it should recognize it's stuck and give up.
So the summary creates false confidence.
That's the best way to describe it. And there's a related problem. Summarization is expensive per call. Each summary processes a unique slice of conversation history, so you get almost no cache reuse. The JetBrains study found summarization calls can account for more than 7% of total cost per instance for large models.
Which is a meaningful overhead if you're running a lot of agents.
And it compounds with the fidelity question. What actually survives summarization? The Anthropic Cookbook is explicit about this. Ticket IDs, categories, priorities, outcomes, those get retained. Full knowledge base article text, detailed classification reasoning, complete drafted responses, those get lost. And when a model is summarizing its own prior work, you get hallucination risk on top of information loss. The model may confabulate details about decisions it made, especially complex technical ones.
There's something recursive and slightly alarming about that. The model summarizes its own previous reasoning, possibly introduces errors, then reasons from that summary, and then that gets summarized again.
It's a lossy compression chain. Each pass potentially introduces drift. Over a long session with multiple compaction events, you could accumulate meaningful distortions. It's an open empirical question how much drift actually accumulates in practice, but the theoretical risk is real.
So what does the hybrid approach look like? Because it seems like you want masking for the common case and summarization as a fallback.
That's exactly what JetBrains proposed and tested. Use observation masking as the primary defense and only trigger LLM summarization when the context becomes truly unwieldy, when masking alone can't prevent overflow. On SWE bench verified with Quin3Coder 480B, the hybrid was 7% cheaper than pure observation masking and 11% cheaper than pure LLM summarization, with a comparable solve rate improvement. OpenHands exposes this natively through their pipeline condenser. You can chain multiple condensers in sequence, remove old events first, then summarize what remains, then truncate if needed. It's a production-ready multi-stage compression architecture.
Now let's talk about the more sophisticated end of the spectrum. Because hierarchical memory is a different paradigm entirely.
TiMem is the most interesting recent work here, published in January 2026 by researchers at the Institute of Automation at the Chinese Academy of Sciences. The core idea is a temporal memory tree with 5 levels. Level 1 is raw dialogue turns, created after each exchange, high fidelity. Level 2 is non-redundant event summaries across a session. Level 3 captures routine context and recurrent interest across a day. Level 4 is evolving behavioral features and preference patterns across a week. Level 5 is stable personality, preferences, and values, updated monthly.
So it mirrors roughly how human memory consolidates over time.
That's the explicit inspiration. Recent memory is kept at high fidelity, older memory is progressively abstracted into patterns and then into a persona profile. And the recall mechanism is complexity-aware, simple queries only search levels 1, 2, and 5. Complex queries traverse the full hierarchy. You're not over-retrieving for simple questions, but you can go deep when you need to.
What are the benchmark numbers?
75.3% on Locomo and 76.88% on Long Mem Evil S, which are the main long horizon conversation benchmarks. 52% reduction in recalled context length on Locomo compared to baselines. It outperforms MemOS, MemOS, MemoryOS, AMEM, and Memory Bank, and it requires no fine-tuning. It's a plug-and-play layer on any LLM.
The no fine-tuning part is significant, because if you need to retrain the model to use the memory system, your deployment story gets very complicated.
There was also a concurrent paper for Ningning Zhang et al. Called HeMem, published the same week in January 2026. They use a dual-channel segmentation strategy. One channel tracks concrete interaction events. The other tracks stable knowledge. The two are linked hierarchically. It's a slightly different architecture, but converging on the same insight. Different types of information should be compressed on different schedules.
Before we get to the UX side of this, I want to flag MemGPT, because it takes a completely different approach philosophically.
MemGPT from UC Berkeley in 2023 is the one that framed this as an operating systems problem. The LLM is like a CPU with limited RAM. External storage is the disk. Information gets paged in from archival memory when needed and paged out when it's not. And critically, the model itself manages what to keep in context via function calls. It's not a separate system deciding what the model sees. The model is an active participant in its own memory management.
Which raises a question about trust. If the model decides what to remember, and the model has primacy and recency biases, then you're letting a biased system manage its own biases.
That's a real concern, though the MemGPT framing is that you give the model explicit memory management tools, read, write, search, and it uses them deliberately rather than relying on implicit attention. The biases are in the attention mechanism. Explicit function calls are a different pathway.
Let's get into the UX question, because I think this is where the discussion gets genuinely interesting from a product perspective. The core tension is, should compression be visible to users, or should it happen silently in the background?
The current landscape is pretty fragmented on this. Web UIs, ChatGPT, Claude.a offer no visibility whatsoever, no context percentage, no indicator that anything is being compressed or lost. Teresa Torres made a sharp observation about this. These tools make it seem like the context window is infinite because you can just keep chatting forever. Most users have no idea that the model's effective memory of the conversation is degrading as the conversation grows.
And that seems actively harmful. Not in a dramatic way, no one's getting hurt, but it creates systematically miscalibrated expectations.
Which is the argument for transparency. Claude Code takes the opposite approach. The context utilization percentage is always visible in the status bar. You can run /compact with custom preservation instructions. You can run /context to inspect what's in the window, /clear to wipe it. The user is in the loop at every stage.
The Mind Studio Guide made a recommendation I found compelling. Compact at 60% utilization, not 95.
This is the summarizing a degraded view. Problem: if you wait until 80 or 95% full to compact, the model is already working with partial compressed information. The summary it generates reflects that degradation. You're not summarizing the original conversation. You're summarizing the model's already impaired view of the conversation. Whereas at 60%, the model still has full uncompressed access to everything, so the summary it generates is based on complete information.
It's the difference between making a copy before the original deteriorates versus making a copy of a deteriorated original.
And the Anthropic SDK data shows the cost savings are real regardless of when you compact. They ran 5 customer service tickets through an agentic workflow. Without compaction, it consumed 208,838 tokens. With automatic compaction enabled, it consumed 86,446 tokens. That's a 58.6% reduction. 2 compaction events triggered automatically during processing.
58% is a meaningful number when you're running thousands of agent instances.
It compounds fast. The compaction mechanism works by monitoring token usage per turn, injecting a summary prompt as a user turn when the threshold is exceeded, having the model generate a summary wrapped in summary tags, clearing the conversation history, and resuming with the compressed context. It's elegant, but there's an important limitation. It doesn't work optimally with server-side sampling loops because cache tokens accumulate and can trigger compaction prematurely.
So it's developer-facing transparency, not end-user-facing transparency. The SDK gives developers control, but that control doesn't propagate to the person actually using the application.
That's the gap. And I think it's the most interesting unsolved problem in this space. You have Claude Code, which gives sophisticated users full visibility and control. You have the Anthropic SDK, which gives developers programmatic control. You have OpenHance's condenser architecture, which is automatic but invisible to end users. What doesn't exist yet, at least not in a mature form, is a consumer-facing interface that shows users their context status, tells them what's been compressed, and lets them specify what to preserve.
And the counterargument to transparency is that most users don't want to think about this. They want to talk to an AI assistant, not manage a database.
Which is a reasonable product instinct. But the Mind Studio Guide identifies a practice that makes transparency feel necessary. They recommend sending a verification message after every compaction. Summarize where we are and what we're working on next. To confirm the post-compaction state matches your expectations. If something important got dropped, you add it back immediately.
That's a workflow that only works if you know compaction happened.
Which is the crux of it. If compaction is invisible, you can't verify. If you can't verify, you're operating on the assumption that the AI remembers everything it needs to remember, which is false, and increasingly false as the session grows.
There's something worth naming here about the trust calibration problem, because there are 2 failure modes. One is the user knowing the system has limits and being anxious about it. The other is the user not knowing and developing false confidence.
And false confidence is the more dangerous failure mode. If I know the AI's memory degrades, I can compensate. I can restart sessions, I can compact early, I can explicitly restate critical constraints. If I don't know, I just assume the AI is tracking everything, and I'm surprised when it contradicts itself or ignores an instruction I gave an hour ago.
The who decides what to forget question is interesting too. Because the options are pretty different in their implications, you've got the model deciding, MEM-GPT style. You've got a separate summarizer model deciding. You've got the user deciding via explicit commands. You've got a rule-based system deciding via sliding window rules. You've got a hierarchical scheduler deciding via temporal boundaries like TiMem.
And each of those has different trust properties. A rule-based system is predictable. You know exactly what gets dropped. A separate summarizer model is opaque, but potentially more semantically intelligent. The user deciding is the most trustworthy from a user perspective, but requires the most cognitive load. The model deciding is interesting because it's the most context-aware, but it's also the most circular. You're asking the model to make decisions about its own limitations.
The Paulson paper from 2025 is worth flagging here because it broadened the scope of the problem. The original lost in the middle research was mostly about needle in a haystack tasks. Find this specific fact. Paulson showed that context degradation affects a much wider range of task types, and often with far fewer tokens for complex tasks. So you can't just say, well, my use case doesn't involve retrieval, so I'm fine.
The complexity of the task matters a lot. A simple factual lookup might degrade at 100,000 tokens. A complex multi-step reasoning task might start showing degradation at 20,000 tokens. The threshold isn't fixed. It scales with task demand.
Which means the engineering answer can't be a single fixed compaction threshold either. You'd want something that's sensitive to what the agent is actually trying to do.
TiMem's complexity-aware recall is a step in that direction, but it's on the retrieval side. On the compaction side, I'm not aware of anyone who's built a task complexity-aware compaction trigger yet. That feels like an open research and engineering problem.
What's your overall read on where this is heading? Because we have academic systems like TiMem with impressive benchmarks, and we have production systems like OpenHands and Claude Code with pragmatic solutions, and they feel like they're on different timescales.
I think the gap closes faster than people expect because the economic pressure is real. A 58% token reduction isn't just a cost saving, it's a capability expansion. If you can run twice as many agent steps for the same budget, you can tackle harder tasks. The teams building production agents have strong incentives to adopt whatever works.
And the JetBrains finding that simple observation masking beats sophisticated summarization in most settings is actually good news for adoption because it's cheap and easy to implement.
The hybrid approach is probably where most production systems end up, masking for the common case, summarization as a fallback for long trajectories, hierarchical memory for applications where long-term user modeling matters. No single strategy dominates across all use cases.
The UX transparency question feels less settled to me. Because the current situation, where sophisticated users in Claude Code get full visibility and everyone else using a web UI gets nothing, is a bit of an accidental divide.
It is. And I think the right answer is something like what Claude Code does, but designed for a less technical audience. You don't need to show users token counts. But you could show a simple indicator. Your conversation memory is getting full. Would you like me to summarize what we've covered? That's transparent without being technical.
And it shifts the decision to the user at the right moment, rather than either surprising them with degraded behavior or burdening them with constant memory management.
The verification practice is the key thing. If you compact and then ask, what do you remember about our goals for this session? That 30-second check catches most of the cases where something important got dropped. That workflow should be built into the interface, not left as a manual step for power users.
All right, practical takeaways. What should someone actually do with this?
If you're using Claude Code for long sessions, compact at 60%, not 95%. Put your most critical constraints in a preservation instruction when you run /compact, and treat the post-compaction verification as non-optional. If you're building agentic systems, start with observation masking before reaching for LLM summarization. The JetBrains data suggests it'll perform comparably and cost significantly less. Only add summarization for trajectories that genuinely overflow masking's capacity.
For anyone using web UIs who doesn't have access to compaction tools, the Teresa Torres recommendation is worth following. Start a fresh chat when you switch topics, when the model does something noticeably wrong, or when the conversation exceeds roughly 15 messages. It's blunt, but it's the only lever you have.
And if you're evaluating memory architectures for longer horizon applications, personal assistants, long-running research agents, anything where the same user interacts across many sessions, TiMem's approach of progressive compression with temporal structure is the most principled framework we have right now. 75% accuracy on Locomo with a 52% reduction in recalled context length is a strong result.
The deeper question that this whole episode circles around, whether AI systems should be honest with users about their memory limitations, feels like it has an obvious answer, but the industry hasn't acted on it yet.
Calibrated trust is the goal. Users who know the system has limits can work with those limits. Users who don't know are just waiting to be surprised. The technology to make this transparent exists. Claude Code proves it. The question is whether consumer product teams prioritize it.
That's probably where we leave it. Thanks as always to our producer Hilbert Flumingtop for keeping this show running. Big thanks to Modal for the GPU credits that power the generation pipeline. Genuinely couldn't do this without them. This has been My Weird Prompts. If you want to find us, head to myweirdprompts.com for the RSS feed and all the ways to subscribe. We'll see you next time.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts, that's the flows from slow